Hello there, Prof here. Welcome to Tech Foundation. This is the third episode of my Electronics 101 tutorials. In this episode, we are going to talk briefly about electronic circuit and circuit elements. Now, this is not going to be an in-depth tutorial on the topic. It is just to give you an idea. I will treat each element in details in later episodes. If you haven't watched my previous videos, then I encourage you to pause this one and go and watch them because it is a build up from the previous video. Okay, let's get started. Electronics is mainly about controlling the flow of electrons, and I keep saying this. This includes which path we want the electrons to flow, how many electrons we want to allow in a particular path, and so on. The path traced by electrons is called the electric circuit. Every electric circuit has a source, which is the point where electrons enter the circuit, and a sink, ground, or return, which also represent the point where the electrons leave the circuit. For almost every circuit we build, there will be a form of load that we want to control or switch. Loads could be as simple as electrical appliances like a light bulb or as complex as a drone. Now, whenever current is passed through any material, there is work done in that material, and this leads to a change in potential difference across the material. Depending on the nature of the material, the voltage drop will be linearly dependent on the amount of current flowing through the material. This is the statement of Ohm's law. Ohm's law states that the current through an ohmic conductor is directly proportional to the voltage drop across the conductor. Please do not confuse voltage drop across a conductor with EMF of the circuit itself. In future videos, I will explain why. So from Ohm's law, we can write that a change in voltage is directly proportional to the amount of current flowing through the conductor. That is, change in V is proportional to I. The constant of proportionality here, as mathematics demands, is the resistance of the material, and again, do not confuse resistance with resistivity. However, Ohm's law has a limitation, which is temperature. A change in temperature has different effects on different materials. Some materials have what we call positive temperature coefficient of resistance. What this means is that as temperature increases, their resistance also increases. Others have a negative temperature coefficient of resistance, meaning that their resistance decreases as temperature increases. Okay, and this is how a thermistor works. Okay, that's how a thermistor works. Yes, so as the temperature increases, its resistance decreases, and we sense that and trigger some action. Okay, so typical examples are semiconductors. Okay, so we will look at semiconductors later, and you would understand this concept in total. All right, so power in electric circuit is the product of voltage and current. Remember also that power is energy per unit time. So for a resistive element, this power is usually dissipated in the form of heat in the material. So this causes a rise in temperature, and hence depending on the temperature coefficient of the material, there will be a change in resistance. For Ohm's law to hold, it requires that resistance remains constant, and this limitation is very important in circuit design. The components of an electric circuit are called circuit elements. Every circuit includes at least one power source and a bunch of elements connected together in a particular fashion to serve a purpose. So circuit elements are either sources or components. Sources provide energy for the circuit. Basically, there are two types of sources. We have voltage sources and current sources. A voltage source usually maintains a fixed voltage while current varies, and a current source performs the opposite. It maintains a fixed current while voltage varies. Circuit components come in three basic types. we have passive components, active components, and electromagnetic components. The concept of passivity is slightly different depending on the field. However, in principle, passive components do not require energy to operate. They include resistors, capacitors, and inductors. Active components, on the other hand, require electric energy before they can operate. Take a diode, for instance. It is a circuit component that allows current to flow in only one direction. We shall talk about diodes and PN junctions in later episodes. Before a diode can conduct, a certain threshold voltage must be reached. The value of this voltage is usually about 0.7 volt for silicon-based diodes. Now, this voltage is called the barrier potential, and I'm not going to talk much about it for now. So, energy is required for the diode to start conducting. The same applies to transistors and integrated circuit elements. Electromechanical components take in electrical energy and generate some sort of mechanical energy or motion. Examples include relays, contactors, DC motors, solenoid devices, etc. Passive components also come in three basic flavors, and this classification is based on their current voltage or IV relationship. That's how the current through them relates to the potential difference across their terminals. By this definition, we can group passive components into resistors, capacitors, and inductors. These components usually have two terminals, so they are sometimes referred to as 222 terminal elements. Now, let's look at what we call ideal sources. Practically, we cannot have ideal sources. However, learning about them is very important. Personally, I love to start with an ideal situation before I impose the physical constraint. Now, an ideal source is a perfect source. They come in two variants. We have ideal voltage source and ideal current source. Ideal voltage sources have a fixed output voltage irrespective of the amount of current drawn from it. Practically, this is not possible. However, we have a range where physical things can operate in ideality. So if we look at the IV characteristic curve here for this ideal voltage source, you realize that it is a vertical line. This means that, for instance, if we set our ideal voltage source to 3 volts, as we've done in here, as we are showing in this graph, then irrespective of the amount of current we draw from it, this output voltage will remain unchanged. Now, for this to happen, it means that the source, which is the voltage source, should have a zero internal resistance, which is practically impossible. When the source has a zero internal resistance, then it means there will be no voltage drop within the source itself. So all the voltage will appear across the load. What we see is that per the design of our constant voltage source, when a certain limit of current draw is exceeded, practically what we see is that per the design of our constant voltage source, when a certain limit of current draw is exceeded, the voltage drops, and this is because of the internal resistance of the source itself. Two symbols are used to represent constant voltage sources. The first one represents a battery. This particular one represents a battery, and the second one represents generic power supplies. The longer bar of this battery symbol represents the anode or the positive terminal, and the shorter bar represents the cathode or the negative terminal. So it means that in respect, there are two cells put together, and when we put cells together, we get what we call a battery. With this principle in mind, we can also talk about an ideal variable voltage source, which is nothing but a source that generates a known voltage as a function of time. Again, no matter how much current is drawn, the voltage remains unaffected. Vt, that is our time dependent voltage here, can be any time varying voltage such as a sine wave or even a square wave. Now let's look at an ideal constant current source. These sources, instead of rather producing a fixed voltage, produces a fixed output current irrespective of the voltage across the terminals. If you look at the IV characteristic curve we have here, we have a horizontal line, and what this means is that no matter how much voltage we draw, the current will still remain constant. And in this case, realize that if we should trace different voltages to this graph, it still crosses the graph at 2 milliamps. Okay, so that is the mathematical representation of an ideal constant current source. Practically, this is also impossible, though within certain limits we can design power supply unit to exhibit ideality. Now, for this to happen, it means that the constant current source must have an infinite output resistance so that no current is consumed by the source itself. So when current is zero, the change in voltage is also zero and all the current is delivered to the load. Since we can't have an infinite resistance, this is not practically possible. I said that passive components can be resistive, capacitive, or inductive. Now let's talk a little bit about them. Resistive elements, we know, oppose the flow of current in circuits. Now what I want you to take into consideration is the phrase the flow of current. This means that it does not destroy the current. Okay, by resisting it, we don't mean that it's maybe has a mechanism for destroying the current. No, it merely reduces the amount of electric charges that flows per unit time. I want you to pay attention to this simulation. Okay, now what does this mean? So we have 4 electrons moving together. Now remember, we defined current as the number of electrons passing through a cross-sectional area per unit time. So at the wider side, 4 electrons were able to pass parallel or together at the same time. Now when it gets to the middle portion, the path narrows and the 4 electrons can no more pass through. So 2 of them went through, followed by the rest. Okay, thus in effect we've reduced the number of electrons passing per unit time. This constriction that we have here represents a resistor. A resistor does not destroy the amount of current passing, it merely reduces the number that can pass per unit time. And since we define current as the number of electrons passing per unit time, so far as we have reduced the number of electrons, it ends up affecting the amount of current that should flow. Certain passive elements are also inductive. Inductive elements are capable of storing energy in magnetic fields. When current flows through an inductor, it generates a magnetic field. According to Faraday's law, when the current flowing through an inductor changes, it causes a change in the magnetic field. So if the current was increasing or decreasing, then it means the magnetic field is going to increase or decrease. Okay, now for a very brief moment, the magnetic field undergoes change, and so we say that it is time varying. Okay, now this time varying magnetic field induces what we call electromotive force or voltage in the conductor. According to Lenz's law, the induced voltage has a polarity or direction which opposes the change in current that created it. As a result, inductors oppose any change in current through them. Now, let me try and explain this in a very simple way. In the first episode, we said that moving charges generate electric field. If you haven't watched that episode, then please go and watch it. Now, whenever current passes through any piece of wire or conductor, there is a magnetic field generated around the wire. So, when we create a coil with the wire, the magnetic field concentrates inside a small area, making its intensity appreciable. When the current through the coil is constant, then we have a constant magnetic field. But take note that Faraday's law will only hold when the magnetic field is changing. Whenever there is a change in magnetic field, it results in generation of voltage in the coils, which according to Lenz's law is opposite the direction of the flow of current in the coil. So in effect, the current is not allowed to change. The ratio of the voltage to the rate of change of current is what we call inductance. The SI unit of inductance is Henry. Now, inductors play roles in power supplies a lot. If you look at the topologies for back convert, those pulse width modulated or switch mode power supplies, we filter or we smoothen the output voltage using inductors and capacitors in combination. Okay, so we shall look at them in details some other time. Certain passive elements too are capacitive in nature. Unlike inductors that store energy in a magnetic field, capacitors store energy in electric field. So capacitors are capable of resisting a change in voltage. So if you've seen a rectification circuit before, you realize that we use capacitors to smoothen the circuit because they have the tendency of resisting a change in voltage. Capacitance is measured in farads, and it is a topic I'm going to treat on its own. So for now, let's just stick with this. Alright, I hope this helps. That is all for this episode. Don't forget to like, share, and subscribe to this channel. I am Prof, and this is Tech Foundation.